Chapter 8. Data Table. Section 1. Structured Data. From this chapter, we begin to learn the tabular data and its processing methods that we deal with every day in our daily work. In the previous example of merging Excel files, we have seen this kind of table. The first row is the title, explaining what is stored in each column. Each row is an item of data which may correspond to a person, an organization, an order, an event, etc. This kind of data has a professional term, which is called structured data. This is the most common data type in modern data processing. The data of the whole table is referred to as a data table, in which each row, except the title, is called a record, the column is called a field, and the string in the title is called a field name. There are 9 records in the visible part of the above table, corresponding to row 2 to 10 of the Excel. There are also 6 fields. The field names are ID, company, area, order date, amount, and phone. Field names are different from each other and can uniquely identify a column. These fields, including name and order, are called the data structure of the data table, or structure for short. Structured data is data with data structure. A2 to F9 in the table is the data in the data table. We will say what is the value of a field of a record. For example, the ID field of the second record is 10248, and the area field of the 8th record is center. Each field of each record in the data table will have a value. Note that only fields in the data table have names, and records have no names. We will talk about how to identify and distinguish records later. There can be various data tables, and the data structure of different data tables can of course be different. A data table must have a set of data structure, and there can only be one. Sometimes we also say the record structure, which means the structure of the data table where the record is located. Because structured data is often presented in the form of this row-column style table, we will also intuitively call records and fields rows and columns. This is a common term in the database industry, not a popular term invented in this book. Sometimes there are no obvious rows and columns when the data table is presented. We will talk about such an example soon. People still use the terms row and column to represent record and field. Structured data in the form of tables is very common in reality, and most readers will have this experience. It is not difficult to understand the concepts of records and fields by looking at a table. We won't give more examples here. However, structured data is not always presented in the form of the above table, it may also be something else. For example, the data from row 5 can be regarded as a data table, but what are the fields? It seems that the contents in row 3 and 4 are the field names, but the string with a space in the middle like item code is usually not suitable for the field name, and it is unclear whether the field names in columns F and G on the right are the contents of F4 and G4. In fact, although SPL supports such strings, it is rarely used, and this book does not intend to cover it. Actually, the contents of row 3 and 4 here can only be regarded as a description of the fields. The real data structure, mainly the field name, is not necessarily the content of the title row seen in the table, but can also be described and set separately. There is also this form. This is no longer in the form of row-column table, but it can still form a data table with 2 records. The fields can be ID, name, position, birthday, phone, address and postcode. So, what is structured data and data table? Look at the above examples. The data in the same Excel describes the same kind of things, such as a person, an order, etc. These things have the same attributes. For example, people have common attributes such as name, sex, birthday, and orders also have common attributes such as customer, date and amount. Each thing is a record, and these attributes are fields. A batch of things with the same attributes constitute a data table, that is, the data table has multiple records and fields. Data table, record and field are abstract concepts, which essentially correspond to something and its attributes. They are not the same as the Excel table. The data table does not have a fixed rendering style that must be observed, but for easy recognition, it is usually rendered as a row-column table and filled with field names in the title. For the data in Excel table, as long as the attributes used to describe a certain kind of things can be extracted, and if there are multiple similar things with the same attributes, it can be considered as structured data. As for what the title content of the table is, whether there is a title, or even whether the table is in row-column form, it is not an important factor. The key is only whether a class of things with common attributes is described. Look at another table. Can we find structured data from here? In other words, can we extract things described by attributes? Yes, but there are two data tables here. The first is in the upper part, describing the basic information of an employee, and the fields include name, sex, birthday, nation, ID card, etc. The second is in the lower part, describing the employee's family members, and the fields include name, relation, workplace, and phone. Employees themselves and family members are two different things with different attributes. A data table can only have one set of data structure and can only describe one kind of things. To fully describe the information of an employee, two data tables are required, that is, employee data table and family member data table. There is another case like this. This looks like a row table, and it should be easy to extract structured data. But what is the data structure? Simply put, we can take each column as a field name, that is, type, west, east and so on. This is indeed a method, but it is not convenient. The computing ability of structured data in the direction of rows and columns, or records and fields, is different. When we want to calculate the sum of various regions, it is troublesome to list the fields one by one, while the statistics on records is much easier. In order to facilitate statistics, for this cross table, we usually design a data table with three fields, type, area, amount. In this way, the statistics in both directions will be relatively simple, and if necessary, the table can be displayed in another way. For example, put area on the row and type on the column, which does not affect the data structure. However, to design the structure like above is not inevitable. It should be determined according to the calculation objectives of the next step. Sometimes it is still designed as type, west, east, etc., which will be more convenient. To find out structured data from chaotic tables, we call this work structure analysis. It is not a very obvious and easy task. We need to design a reasonable data structure according to different conditions and objectives. Structure analysis is also a very important work. If the data is not structured, it is difficult to implement further calculation, and the data that cannot be calculated is meaningless. Of course, structured data is not always stored as Excel files. Conversely, the data stored in Excel is not always structured data. In fact, the most structured data is stored in the database. However, the knowledge of database is too professional to be covered in this book. In daily work, in addition to Excel files, text files are also commonly used to store structured data. There are two common formats, TXT and CSV. Text files usually correspond to one record per line. Usually, the first line will be the title, usually the field names. The columns of text files are separated by tabs, \T, while CSV files are separated by commas. The text file is obviously not as neat as Excel in display, but it will not cause the field dislocation of the record. Section 2. Table sequence and record sequence. With the basic concept of structured data, let's learn how to process this data, that is, the second half of the book mentioned in the preface. Among the programming languages used to process structured data, SQL is the most widely used at present. The full name of SQL is Structured Query Language, which means the language specially used for structured data query. It is the common language of relational database. Except for SQL-related materials, most programming books do not talk about structured data. After talking about the content equivalent to the first half of this book, they begin to turn to more advanced object-oriented content. For non-professionals, this book can be said to have ended. However, learning to this level, except for doing some math problems of primary and secondary schools to practice our brains, just like the examples mentioned above, it will not be of any substantive help to our daily work. Only after learning the knowledge and skills of structured data can we really use programming to improve work efficiency, which is also an important goal of this book. However, this book is not going to talk about SQL. There are a lot of materials in this area. If you are interested, you can learn it yourself. SQL usually can only be used in the database, and the skill requirements for installing and administrating a database are a bit high, which is not suitable for the readers of this book. We continue to use SPL. Compared with SQL, SPL has much richer structured data processing capabilities. In most cases, the code is more concise than SQL, and the environment does not rely on the database, which is more suitable for non-professionals. In fact, the full name of SPL is Structured Process Language, which is also invented to process structured data. Structured data is very common. Most data processing tasks in daily work are related to structured data, and it is necessary to invent a more efficient program language. Actually, SQL is allowed to be used for file data in SPROC. The basic SQL function is realized as a special statement of SPL. You can also learn SQL with SPROC without installing the database. Back to the subject, let's first look at how to create a data table. The create function creates an empty data table. The data table must have a data structure, that is, field names, and fill them in the parameters of the create function in turn. The newly created data table has no records. When viewing the data, we will see that there is only a header on the right. Let's write the code more completely and add some data. Create a data table in A5, and then use the record function to fill in the data in C5. We talked about the writing method of A1 to D4 in square brackets earlier. The record function is used to fill the members of the sequence that act as parameters into the data table as field values. The sequence members will be filled in according to the field order in the data structure. After filling in a record, if there are remaining sequence members, a new record will be created for the data table to continue to fill in the remaining sequence members. Now view the data. This looks very similar to the sequence values, only that a sequence is displayed as one column, and the data table is displayed as multiple columns, and each column has a field name. SPROC will also automatically display an index column on the left to facilitate counting. Does it seem to be a more complex sequence? We can indeed understand the data table in SPL as a sequence with records as members. It is still a little different, and we'll talk about it later. In fact, the formal name of the data table in SPL is table sequence, because SPL places great emphasis on the order of records in the table. For people who are used to Excel, it is natural for records, that is, rows, to have order, but for database programmers, the records in the data table are orderless. SPL emphasizes order to distinguish it from SQL. A data table is called a table sequence, but records are still records and fields are also fields. Since a table sequence is a sequence composed of records, can records be obtained by referencing members in the sequence? Yes, we can continue to write the code. Look at the value of A6 after execution. It is still displayed as a table with header, but there is only one row of data, and there is no index column on the left. This is a record. It has a data structure, i.e., fields. Each of its fields has a value, which is listed above. A5 is really like a sequence. It can correctly execute code such as A5.m-1, and A5.len is okay. Let's study the record. Can we get the field value of the record to participate in the operation? Continue writing. Use the dot operator followed by the field name to get the field value. The BMI of the first person Jong-san is calculated in A7, and the height of the third and fourth person is compared in A8, and the name of the taller person is displayed. Can we change the field value? It's okay too. Field values can be referenced and modified by using the extracted record variable C6 and the direct table sequence member A54. For the field f of record r.f is equivalent to a variable with slightly complex name, which can be freely referenced in the expression or assigned. We can see that in SPL, we can get a record from the table sequence to view and calculate separately. Don't take this for granted. This is not allowed in SQL. A SQL record cannot be calculated independently outside the data table. Review the object concept we talked about earlier. Complex data types are not stored directly in variables, but only one address. A record has multiple fields, which seems a little complex. Is it the same? Just do some experiments. The record is also an object. Not only the address of the record is stored in the record variable, but also in the table sequence without copying the record value. Modifying the field value of a record will affect all subsequent codes that reference this record field. As for the table sequence, it is obviously an object. Moreover, a record has more special features. We deliberately fill the data in row 4 and row 2 exactly the same, and then observe the calculation results of the three logical expressions in row 6. The results of A6 and C6 are unpredictable, and multiple executions may get different results. B6 is always false. What's going on? The fields of a record are not always the same kind of things like the members of a sequence. It is usually meaningless to use the field order to compare two records. For example, the name field precedes sex here, but there is no reason that name should take precedence over sex in comparison. However, it is not necessary to return an error, so SPL specifies that the internal address value is used for record comparison, so A6 and C6 will get unpredictable results. As for two records of the same table sequence, even if the contents are exactly the same, they will be allocated memory space respectively, and their address values are also different, so the two different records will never be equal. Then, what can we do if we just want to compare whether the field values of two records are equal, or we just want to compare the records according to the field order? SPL provides special functions for such comparison. We'll get a definite result now. The difference is that the comp function does not return true or false, but an integer. If it is equal, it returns 0, if the former is smaller, it returns -1, if the former is larger, it returns +1. There are three cases in a comparison. Why doesn't SPL directly stipulate the comparison of records as the calculation result of comp function? Comparing the records according to the rules of comp function is not a common operation. It doesn't matter if it's a little troublesome. Comparing whether the address stored in a record variable is the same to determine whether it is physically the same record is a relatively common operation which is often performed implicitly, such as the grouping operation to be discussed later. If the record comparison is stipulated as the result of comp operation, the action of comparing addresses will be much more troublesome or inefficient. Therefore, the SPL convention of the current rule is the result of weighing the computational efficiency and code complexity. A table sequence is like a sequence composed of records. Can we use the insert and delete functions to add and delete members like a sequence? Delete is okay, but insert is different. This is the key difference between a sequence and a table sequence. As we said, a data table has only one set of data structure. When adding a record to the table sequence, it must be a record with the same data structure. If it is allowed to grab a record and insert it into the table sequence, we need to check it in detail to avoid this situation. Moreover, this may cause a record to belong to two different table sequences. When one table sequence adjusts the data structure for some reason, it may lead to the inconsistency of the data structure in the other table sequence. This is too troublesome and seriously affects the efficiency of the program. Therefore, SPL stipulates that a record must be generated from a table sequence and cannot be inserted into other table sequences. In this way, the records of a table sequence are all under the control of the table sequence. There will be no record that comes to another table sequence, and there will be no record that comes from others. Therefore, we will find that SPL provides a function to create a table sequence, but there is no function to create a separate record. After a record is created, it can participate in other operations outside the table sequence, but it must be attached to a table sequence when it is created. A single record created is essentially a record in a table sequence with only one record. This table sequence can continue to insert new records. This can also explain the above, different records will never be equal. The insert function of the table sequence is made as follows. The first position parameter of insert has the same meaning as that of sequence insert. A record can be inserted in the middle or appended at the end. Then write each field value of the record to be inserted in the remaining parameters. SPL will create a new record in the appropriate position of the table sequence and fill in the field value. The purpose of assembling members into a sequence, that is, a set, is to facilitate operation and processing together. For example, we can use the loop function mentioned above. If the records of the table sequence must exist in the table sequence, can the records of different table sequences be put together for operation? Moreover, even if it is the same table sequence, not all the members may participate in the operation at one time, and a sequence has a method to get a subsequence. Is this still valid for the table sequence? These operations are allowed in SPL. Records are only attached to the table sequence when they are created to ensure the consistency of their data structure. Once created, they can be referenced and combined freely like ordinary data. It is very common for a sequence composed of a batch of records from different table sequences, or a sequence composed of partial records of a table sequence. This sequence has a special name in SPL called record sequence. Of course, a record sequence is also an object. For the loop functions of table sequence and record sequence, we will talk about them later. Now we will manually create several record sequences. At present, we have only one table sequence at hand, and can only create record sequences composed of the records of this table sequence. Note B6 that the member of a record sequence can be referenced from another record sequence, not necessarily directly from the table sequence. Moreover, its members can be repeated, and B7 will calculate true. The members of the table sequences cannot be equal to each other because they are newly created every time, while different record sequences can of course be composed of the same record, and C7 also calculates true. A record sequence can be understood as an ordinary sequence, because it may have same members, and the set operations are also meaningful. The result of these set operations is still a record sequence, and the table sequence itself can be regarded as a record sequence composed of all its records, and can also participate in these set operations, but the calculation result will no longer be a table sequence, but just a record sequence. Now let's do the problem of merging Excel again. Since we haven't learned to change the data structure, we reduce one requirement, only merge the data without adding the file name to the end. We have understood A1. This time B2 uses the XLS import function without @w, which will read the file into a table sequence. @t indicates that the first row of the file is the field names of the table sequence. B3 in the loop body concatenates the table sequences read each time, which will form a sequence composed of records from multiple table sequences, that is, a record sequence composed of records from multiple table sequences. After the concatenation, just write it in A4 with XLS export function. @t also means to write the field names to the first row as the title. This code is much simpler than the previous string processing, and there is no need to deal with the disassembly and assembly of the title. In fact, using loop function can be simpler. Multiple record sequences can also form a two-layer sequence, and then concatenate into one using conjunction function. This code requires that the merged Excel files have the same data structure, i.e. the same columns. In fact, a record sequence does not require that all member records have the same data structure. There will be no problem as long as there is no error when referencing fields. However, this situation is very rare, and we won't give an example. Section 3. Generation of table sequence. In order to further learn the operations of record sequence, we need a table sequence with a little more records, such as the table sequence with 4 fields we used earlier: name, sex, weight, and height. It is much more convenient to generate hundreds of records and do experiments again. Obviously, it is too troublesome to manually fill in the field values of many records. We use a program to generate them. The specific values of the fields do not affect learning. They can be generated randomly. We can already do this with the code technology we have learned now. The meaningful name is troublesome, so we use the number string instead. C2, B3, C3 are easy to understand, and then in B4, insert the generated fields into the empty table sequence created in A1. After the code is executed, we can get a table sequence with 100 records. There's nothing wrong with this code, but it's still a little troublesome. We've learned loop functions, and it's easy to think that there should be a loop function to solve this task. However, the loop function 100.x used to generate a new sequence can only return a sequence, which is not what we need. SPL provides a loop function to return a new table sequence. The above code can be simplified into one statement. It's a little long, so it's written in 2 lines. The statements related to structured data are often very long. This is also the advantage of using a cell to write code. It won't let too long code in a cell to write out of the cell and affect the code reading on the right and below. Similar to a.x returning a sequence with the same length as a.new will return a table sequence with the same number of records as a.len. It also generates a record for each member of A, and these records will form a table sequence and return. The new function is a little different in the way the parameters are written. It is obvious that each field is separated by a comma. The calculation formula of the field value is before the colon and the field name is after the colon. Is this colon a special provision of the new function? Yes and no. After we are dealing with structured data, we often face more complex function parameters. For example, to execute the new function correctly, we need to know the value calculation formula and field name of each field in the table sequence to be generated, and the field value calculation formula and field name are a pair and cannot be misplaced. With the current new function, the field value formula and field name are always a group of 2. If we still use the comma-separated writing method, we can still use the position of the parameter to determine the corresponding relationship, but it already looks dizzy. If the number of parameters in each group is uncertain, there is no way to correspond at all. In fact, the new function does allow that field names are omitted. In many cases, it can automatically identify a reasonable field name. If the field names are to be written every time, it will be very troublesome. In this case, one way is to use the set as a parameter. For example, this new function can be written as. The parameters here are divided into 4 groups. Each field is a group, and each group has 2 members, namely, the calculation formula and the field name. In this way, the corresponding relationship between parameters can be described clearly. If the field name is not written, the result is that a group has only 1 member and will not be misaligned with the parameters of other groups. This is the concept of multi-level parameters. The parameters written in the function should be divided into multi-level groups to ensure a clear description of the corresponding relationship between these parameters. Theoretically, there may be more levels, so braces may be nested, which still looks a little messy. SPL does not adopt the writing method of nested braces, but the convention only supports 3-level parameters, separated by semicolons, commas and colons respectively. Semicolons are the first level. The semicolon-separated parameter is a group. If there are lower-level parameters in this group, they are separated by commas, and the next-level parameters are separated by colons. There are 3 levels in total. Practice shows that 3 levels are basically enough, and there is rarely any parameter relationship that cannot be described clearly with this method. While using commas only is often ambiguous. In fact, we have seen semicolons when we talked about the top function, but we haven't analyzed them carefully. Multi-level parameter syntax is also the invention of SPL. It is not designed only for structured data calculation. It will also be involved in conventional numerical operations, but it often appears due to the complexity of structured data processing. If you have learned SQL, you can compare it. Each part of SQL separated by keywords can also be understood as multi-level parameters. Only that pretending to be English will have better readability, but its universality is much worse. You should select special keywords for each statement. The complexity of structured data will force multi-level parameters to appear. After understanding the multi-level parameters, the new function above is easy to understand. The colon is indeed required for the new function parameters because it has 2 levels of parameters, but it is not deliberately specified for the new function, but a general rule in SPL. The insert function of the table sequence also has multi-level parameters. Field names can be specified during insertion. Fields not listed in the parameters will be filled with null after insertion. For example, we need to add 100 records just created with the new function to the previous table sequence with 4 manual records, but only fill in weight and height, and let the others be null. In practice, structured data often has many fields, and it will be more troublesome if the default writing method is not allowed. Similar to the sequence, the insert function of the table sequence can also insert multiple records in batch at one time. Multi-level parameters can easily express various intentions in one pattern. Now we have a table sequence with 100 records, and each record corresponds to one person. We want to get a new table sequence with one more field to store the BMI of each person. With the new function, it is easy. As a loop function, tilde in a1.new is defined as the current member when the sequence loops, that is, a record of table sequence A1. Then we can use the syntax of tilde.f to refer to the field of record tilde. However, A2 written in this way is a little long. SPL stipulates that in the loop function of a table sequence or a record sequence, the field name can be directly used to refer to the field of the current member without writing tilde dot, that is, name is tilde.name, sex is tilde.sex. Moreover, as we said earlier, the new function can sometimes omit the field name, and it can be omitted when the current formula and the field name of the target table sequence are the same. In this way, A2 can be written as. This makes it look much clearer and less error-prone. This kind of appending fields to the end is very common in structured data processing. SPL simply provides a function to process, and the code can be simplified too. The derive function will append new fields based on the data structure of the original table sequence, and all the fields of the original table sequence will be copied. It should be noted that the derive function will create a new table sequence without changing the original table sequence. It will copy all the fields and values of the original table sequence, and the original table sequence is still there. In fact, the derive function can be executed for a record sequence, not necessarily for a table sequence. The new function will of course create a new one, and it can even be executed for a sequence rather than a record sequence. Now, we can restore the problem of merging Excel to the previous requirement, append the file name to the end. The statement is a little long, and we wrote one more line. Actually, all actions can be written in one statement. For the table sequence read out by each file, use the derive function to append a file field to the end, and the value is the current file name. It should be noted that derive is a loop function, and the tilde written directly in its expression refers to the current record of the table sequence or record sequence. Here, when adding a file name, we should use the upper layer tilde, that is, a1.tilde. Section 4. Loop functions. Since record sequences can be regarded as sequences, we should also be able to use loop functions for these objects. We have used new and derive functions. Let's try the loop functions we learned before and continue to use the table sequence of 100 records created with new function. Calculate the average height, maximum weight and minimum BMI of these people. Taking a record sequence as a sequence, the a.x operation can be performed normally. It is often used to get the sequence composed of values of a field. Structured data has multiple fields, so it is easy to form some expressions with business significance. Therefore, aggregation functions based on record sequence will often be calculated directly with an expression like B2, B3, and A4 here. The selection function for structured data will also be more business meaningful than for conventional data. Find the person with the largest weight and the person with the smallest BMI. A2 only finds the first and return, and B2 uses at A to find all the records that maximize the weight. This is often what we are more concerned about, that is, the record corresponding to the maximum and minimum value, rather than the maximum and minimum value itself. The record selected by conditions can also perform various set operations as well as further aggregation and selection operations. A2 selects the persons whose height is not less than 1.7 and B2 selects the females. A3 calculates the intersection of the two. B3 uses logical operation to express the same calculation result as A3. It is the similar case with A4 and B4. A5 and B5 do further selection to the selected record sequence, and A6 and B6 continue to do aggregation to the selected record sequence. Sorting is also a common operation. We know that the default sorting direction of the sort function is from small to large, and we can use etc to reverse the order. However, when it comes to structured data, there are often multiple fields to sort, and the sorting directions of these parameters are different. In this case, there is no way to use only one etc to control. The method given by SPL is to write the parameters as opposite numbers by adding a negative sign, so that if we continue to sort from small to large, we will realize the reverse order of the original values. The method of writing the opposite number with a negative sign is also applicable to string and datetime data. In this way, A2 sorts by height from low to high, and B3 sorts females by weight from large to small. A4 will sort by height from small to large first, and those with the same height will be sorted by weight from large to small. Using negative numbers in the top function is another way to represent the reverse order, which is equivalent to getting the last few after sorting. If using positive numbers, it means to get the first few. A5 and B5 will calculate the 3 largest weights and the 3 individuals with largest weights respectively. The calculation result of A5 is a sequence composed of 3 numbers, while B5 returns a record sequence composed of 3 records. SPL also supports ranking function. The ranks function in A6 can calculate everyone's ranking by height. We feel that using male and female to represent gender is too long. Just use one letter M and F. In the future, it will be shorter when writing comparative expressions. It can be done with the run function. When using the loop function to assign a value to a field, we can also directly use the field name to represent the field of the current record instead of writing as tilde.sex. Derive function can be used to append fields to generate a new table sequence. Sometimes we need to append multiple fields, and the field to be appended later needs to be calculated from the field to be appended first. For example, we need to add a BMI field, and then add a flag field for obesity according to the value of BMI. With derive function, it will be written like this. However, the calculation of derive function is very complex. It needs to create new records and table sequence and copy the original data. The performance is poor. In principle, it should be used as little as possible. A better way is to use derive function and run function to complete the task. Append both fields at one time in A2, and then use run function in A3 to calculate the value of flag field. The derive function is executed only once, and the actions of creating and copying table sequence are reduced, and the operation performance can be improved a lot. From these examples, we can realize once again that multiple fields of structured data are easy to form many calculation expressions with business significance. There are many operations on field expressions in loop functions, but they are relatively uncommon in single-value sequence calculation. Combined with the functions of reading and writing Excel files, we can now use program code to merge, filter, add calculation results, sort and perform other operations on a batch of Excel files. Similar to the loop function of a sequence, the record sequence will also have multi-layer nesting. For example, we want to calculate the minimum height difference between males and females in this group. When the inner layer needs to reference the record field of the outer loop, the corresponding variable name of the outer loop function should also be written to represent the current record, and it is still not necessary to write tilde. To find out which pairs of male and female make the minimum height difference true, it is more troublesome. Here, we need to use tilde in A3 to keep the record, form a male and female pair, and then find it with the selection function. A3 in B3 is no longer a record sequence, and it is meaningless to reference field names if tilde is omitted. The members of a record sequence are records with multiple fields, and the information content is relatively rich. The result obtained by the selection function is also a record sequence composed of these records. Therefore, the information contained in the position returned by positioning functions such as pSelect, pMax and pMean is seldom needed, but the position still needs to be obtained when it comes to order-related calculations. Now let's discuss the loop functions related to order and regenerate a date-related table sequence. Randomly generate a price table of a stock from 100 days ago to today. DT field is the date and price field is the price. Because there is no transaction on weekends, filter out the weekend dates after generating the data, and use this A2 in the future. The day at W function returns the weekday of a date, but note that its return value is 1 on Sunday and 7 on Saturday. For historical reasons, the computer system uses the habit of Westerners. Sunday is the first day of the week. First, we want to calculate the daily increase and moving average price. In the loop functions of a record sequence, we can add plus or minus I enclosed in square brackets after the field to refer to the field of an adjacent record, and add A to be enclosed in square brackets to refer to the sequence composed of the field values of adjacent records. These are the same as the loop functions of the sequence. Calculate the maximum consecutive rising days of this stock. According to natural thinking, first fill in 0, add 1 if it rises 1 day, and clear to 0 if it does not rise. We can calculate the days of continuous rise to 1 day, and then get the maximum value. Calculate the increase on the day when the stock price is the highest. Here, use the positioning function Pmax to calculate the sequence number where the maximum value is located, and then use this sequence number to calculate the increase. If we need to consider that the highest price may appear on multiple dates, use the at A option. First, calculate the sequence composed of the record sequence numbers where the maximum value is located, and then generate a two-field sequence with new function based on this sequence, taking the date and gain as the fields. In this case, new function can also omit the field name. You can see what the field names of the generated table sequence will be. Similarly, calculate the average increase on the days when the stock price exceeds $90. For this cross-row calculation for a certain position, SPL provides a positioning calculation function. The previous code can also be written like this. The positioning calculation function calc allows the syntax of tilde, hash, square brackets, and so on in the loop function to be used in the non-loop function. The calc function can also be used for sequences, but there are few business meaningful scenarios when structured data is not involved, so we give some examples here. Section 5. Calculations on the fields. As we said earlier, the ability of structured data in row and column directions is asymmetric. Convenient batch operations are usually only provided for row direction, and columns always appear as independent individuals. However, we also need to perform some overall operations in the column direction sometimes, that is, to process a batch of fields together as a set. Let's do the problem of merging Excel again. Change the requirement, spell the file name in front of all columns. The derive function can only append fields to the end. To change the order of fields, we can only recreate with new function for the present, and we need to know what fields are already in the table sequence and copy them again. The fname function can return a sequence of field names in the table sequence, that is, a sequence of strings. But this is not enough. Even if we concatenate the new field to the front, we still don't know how to write this new function, such as this code. A1 is table sequence, A2 gets its field name sequence, but A3 is meaningless. SPL will generate a field named A2, and its value is the current cell value of A2, that is, the field name sequence of A1. When SPL executes here, it does not know to concatenate the value of A2 into this code, but will execute the two characters A and 2 as part of the code. What should we do? SPL provides the syntax of dynamic program. The above code is written like this, and it can be executed correctly. We have used the concat function. It will concatenate a string sequence with the specified separator, and here we use commas. Here A1 has three fields A, B, C, and the calculation result of A2 is the string ABC. The meaning of $sign and braces in A3 is to tell SPL to calculate the expression in braces, which will be a string, then spell the string as part of the statement and then execute it. A2 is now ABC, and $sign and A2 in braces will spell this string into the statement in A3. As a result, the actual statement to be executed by A3 is. This is what we want. The syntax of $sign and braces is called a macro. Using macros, we can dynamically spell some code to execute and achieve a very flexible operation effect. Calculations related to uncertain number fields often use macros. Using macros, we can solve the problem of spelling the file name to the front in merging Excel. Concat at C means to separate by commas. A calculation expression can be written in $ and braces as long as the calculation result is a string. Using macros, we can easily generate the student score table. The calculation result of A2 will be a string like this. After spelling into A3, we will get a score table of 100 students, and the ID field is the student number of the student. Now we want to calculate a total score field, total, for each student and append it to the end. Of course, it's okay, but if there are many subjects, it's hard to write. SPL provides a method to convert record fields into a sequence, and it is much more convenient when field values need to be processed in batch. A .array function gets the field values of record R to form a sequence and return. In this way, no matter how many subjects, the code is like this. It should be noted that since the data types of each field value may be different, the return value of array function may not be a sequence composed of members of the same data type. With macros, we can also complete more complex tasks. All of the Excel files we have previously processed are in row format. However, just as we talked about the concept of structured data, many Excel files storing structured data are not in row format, such as this file. This is part of the previous example. There is only one record to simplify the problem. Suppose there are a batch of such files, each file stores a person's information. Now we hope to extract these data and make a row table using the field names in this table: ID, name, sex, position, birthday, phone, address, postcode. If there are hundreds of such files, it will obviously be too tiring to do it manually. We use a program to do it. To do this, we also need to use two Excel-related functions, XLSOpen and XLSCell. The XLSOpen function can open an Excel file to form an Excel object, and the XLSCell function can read the content of a cell from the Excel object. With them, we can finish the work. The code logic is not complex, and we will not explain it in detail. However, it is still a little troublesome to write, and if the table style and data structure change, it needs to be changed a lot. We use macros and loop functions to simplify it. The fields and corresponding cells are made into two sequences, and it is much easier to get data from each Excel file and do concatenation. The code is not only shorter, but also more general. If we encounter a new format, just modify the first two lines. Conversely, we may use the data of a row table to generate multiple such freestyle Excel. Obviously, doing it manually will also be very tiring. We still use a program to complete this task. We need to learn a little more knowledge. The XLSCell function can also fill data into a cell of an Excel object, and then learn an XLSWrite function, which can write the processed Excel object into a file. First, make a template Excel file in this format, read it into an Excel object, and then fill the relevant values into the Excel object for each record, and then write it into a file. Fill them in and write it out repeatedly, and it's done. When doing artificial intelligence tasks, we often encounter the problem of filling in missing values, that is, filling in the missing data according to certain rules, such as mode or average. Let's try this task. Suppose the file data.xlsx stores the original data. The blank part indicates missing. Our rule is, if this column is an integer, fill it with the mode scheme. If it is a floating point number, it is filled with the average scheme. Read the data into table sequence A1, A2 loops through each field. The field function in B2 will get all the values of a certain field of all records to form a sequence. It is a bit like A1.x, but the difference is that the parameter of the field function here is a string, while x in A1.x is a field name. If it is written in A1.x, a macro needs to be used, and it should be written as A1.$A2. Calculate the sum of the whole column, compare it with the sum of the integerized members. If it is equal, it can be regarded as all integers, then execute the mode scheme, otherwise execute the average scheme. The mode function can return the mode of the sequence. Then calculate the field value sequence after filling in the missing values in B5. The field function can also fill the sequence into the field. Here, it can also be written as A1.run $A2 equals B5 hash in macro, but it is obviously clearer and simpler using the field function.